In 2017, a paper with a provocative title emerged from Google, "Attention is All You Need." It proposed abandoning the dominant paradigm of recurrent neural networks entirely. The result? The transformer architecture that now powers ChatGPT, Claude, DALL-E, and virtually every major AI system today. This single paper sparked a revolution that fundamentally transformed artificial intelligence. Let's understand exactly how it works. Before transformers, sequence-to-sequence tasks like machine translation relied on recurrent neural networks. RNNs process inputs one step at a time, maintaining a hidden state that carries information forward. But this sequential processing creates a fundamental bottleneck: you cannot parallelize computation across sequence positions. For a sentence with 100 words, you must perform 100 sequential operations. This made training extremely slow on modern GPUs designed for parallel computation. RNNs also struggle with long-range dependencies. Information from early in a sequence must pass through many processing steps to influence later outputs. With each step, the signal degrades. If your model needs to connect the cat that sat on the mat near the window with was sleeping, it must maintain that connection across multiple intervening words. LSTMs and GRUs improved this but didn't solve it entirely. The transformer team asked, what if we could connect any two positions directly? Attention allows each position in a sequence to directly attend to all other positions in a single step. For every position, we compute three vectors: a query, representing what information this position is looking for, a key, representing what information this position offers, and a value, containing the actual information to be retrieved. We compute attention by taking the dot product of queries with all keys, applying softmax to get weights, then using those weights to combine values. This gives us scaled dot product attention. A single attention function can only focus on one type of relationship. But language is complex. We might need to track subject-verb agreement, coreference, semantic similarity, and syntactic structure simultaneously. Multi-head attention solves this by running multiple attention functions in parallel. Each head learns to attend to different aspects of the input. The outputs are concatenated and projected back to the model dimension. With 8 heads, the model can maintain 8 different attention patterns simultaneously. The complete transformer consists of an encoder and decoder, each made of stacked layers. The encoder layer has 2 subcomponents: multi-head self-attention, followed by a position-wise feed-forward network. Each subcomponent uses residual connections and layer normalization. The decoder is similar but adds a third component, cross-attention, that attends to the encoder's output. This allows the decoder to focus on relevant parts of the input while generating each output token. Unlike RNNs, the transformer has no inherent notion of sequence order. If we shuffle the input tokens, attention would produce the same outputs. To inject position information, the authors add positional encodings to the input embeddings. They use sinusoidal functions at different frequencies, sine for even dimensions, cosine for odd. This allows the model to learn to attend to relative positions, since for any fixed offset, the positional encoding can be represented as a linear function of the current position. Let's trace through self-attention computation concretely. Given input embeddings, we multiply by learned weight matrices to produce queries, keys, and values. The attention scores are computed as Q times K transpose, divided by the square root of the key dimension. This scaling prevents the softmax from becoming too peaked when dimensions are large. After softmax, we multiply by values. The entire operation is highly parallelizable. All positions can be computed simultaneously using matrix multiplication. After attention, each position passes through a feed-forward network independently. This is a simple 2-layer MLP, linear transformation, ReLU activation, then another linear transformation. The inner dimension is typically 4 times the model dimension. While attention allows positions to exchange information, the feed-forward network processes each position's representation individually. Research suggests these layers act as key-value memories, storing factual knowledge learned during training. The decoder has a crucial constraint: when generating position I, it can only attend to positions before I. This is called causal or masked self-attention. We implement it by setting attention scores to -infinity for future positions before the softmax, effectively zeroing out those connections. This ensures the model cannot cheat by looking at future tokens during training. The masking pattern forms a triangular matrix, enabling efficient parallel training while maintaining autoregressive generation. The transformer's key advantage is parallelization. For sequence length n, RNNs require O(n) sequential operations. Transformers require only O(1) because all positions compute simultaneously. The trade-off is memory. Self-attention requires O(n) superscript 2, memory for the attention matrix. But on modern GPUs optimized for parallel computation, this is a winning trade. The original paper trained models on 8 GPUs for just 12 hours to achieve state-of-the-art translation quality. Previous approaches took days or weeks. The transformer achieved remarkable results on machine translation benchmarks. On English to German translation, it reached 28.4 BLEU score, surpassing all previous models including ensembles. On English to French, it achieved 41.0 BLEU, setting a new state-of-the-art with substantially less training cost. The model also showed strong performance on English constituency parsing, demonstrating its generalization beyond translation. These results prove that attention truly is all you need. Examining learned attention patterns reveals fascinating behavior. Different heads learn distinct linguistic functions. Some heads track syntactic dependencies, connecting subjects to verbs across long distances. Others perform anaphora resolution, linking pronouns like it to their reference. The model learns these patterns without explicit linguistic supervision, discovering language structure through the translation objective. This interpretability is a key advantage over the black box hidden states of RNNs. OpenAI took the decoder-only architecture and scaled it dramatically. GPT-1 showed that pre-training on large text corpora produced useful representations. GPT-2 demonstrated emergent capabilities at scale. GPT-3 with 175 billion parameters showed that transformers could perform tasks with no training examples at all, just instructions in natural language. ChatGPT brought this technology to the masses, fundamentally changing how we interact with computers. Google took the encoder architecture in a different direction with BERT, bidirectional encoder representations from transformers. By masking random tokens and training the model to predict them, BERT learned rich bidirectional representations. This revolutionized NLP tasks like question answering, sentiment analysis, and named entity recognition. The encoder-only architecture excels at understanding and classification, while decoder-only excels at generation. The transformer architecture transcended its origins in language. Vision transformers treat images as sequences of patches, applying the same attention mechanism to visual data. DALL-E and Stable Diffusion use transformers to generate images from text descriptions. Multimodal models combine vision and language transformers to create systems that can see and speak. The architecture proved to be a universal computational primitive for intelligence. The transformer paper introduced a simple but powerful idea: replace sequential recurrence with parallel attention. This architectural choice enabled the scaling revolution that followed. Today's largest language models are direct descendants of this 2017 paper. The 8 authors, Vaswani, Shazeer, Parmar, Uszkoreit, Jones, Gomez, Kaiser, and Polosukhin, created a foundation for modern AI. Attention truly was all we needed to unlock a new era of artificial intelligence.